Welcome back to Geology Watch. When we think of the Atlantic Ocean, we think of a passive, growing basin, quietly separating the continents. All the world's seismic violence, the megaquakes and tsunamis, is thought to belong to the Pacific Ring of Fire. This assumption is dangerously wrong. Just this year, in early 2025, a scientific paper analyzing new high-resolution seafloor maps has confirmed what some geologists have long feared. Hidden within the Atlantic crack is not one, but a series of massive faults, similar in nature to the San Andreas Fault in California. A new analysis of one of these segments, the Charlie Gibbs fracture zone, shows that it is fully locked and has accumulated enough stress to rupture in a catastrophic magnitude 8.0 or larger earthquake. This isn't just a distant geological curiosity. Such an event is the perfect trigger for a secondary disaster, a massive transoceanic tsunami aimed at North America and Europe. Before we explore the details of this hidden threat, if you find these geological updates critical for understanding our planet, please take a moment to like this video and subscribe to Geology Watch. The massive crack in the Atlantic is, of course, the Mid-Atlantic Ridge. It is the longest mountain range on Earth, stretching over 16,000 kilometers. It is a divergent boundary, the seam where the North American and Eurasian plates are torn apart by forces deep within the mantle. Magma constantly rises to fill this gap, pushing the continents apart at a rate of about 2.5 centimeters per year. This entire process is intensely volcanic. This ridge is not a clean break, but a colossal chain of underwater volcanoes and volcanic islands, including Iceland and the Azores. But here is the detail that is almost always overlooked. The ridge does not spread evenly. It is broken into hundreds of individual segments, offset by massive geological scars. These are the fracture zones. If the ridge segments are where the crust is created, the fracture zones are where the plates grind against each other. They are massive transform faults, operating exactly like the San Andreas Fault. While the plates on either side pull apart, the segments on opposite sides of this fracture are moving in opposite directions. This generates enormous strike-slip stress. The new study, published by an international team of oceanographers and seismologists, focused on the Charlie Gibbs fracture zone, a massive 2,000-kilometer-long system that slices the North Atlantic south of Iceland. Using deep-sea sonar, they mapped this fault system in unprecedented detail. What they found is alarming. While many segments of these Atlantic transform faults creep, moving slowly and steadily, releasing stress in small, harmless earthquakes, other segments are completely silent. The new data confirms that a massive segment of the Charlie Gibbs Fault is fully locked. It is stuck. For decades, possibly over a century, the surrounding plates have continued to move, but this specific segment has held, accumulating an immense amount of strain. This is, by definition, a mature seismic gap. This is not just a theory. We have proof of the power these Atlantic faults possess. In 1941, a massive magnitude 8.1 earthquake ruptured a similar transform fault further south near the Azores. This event was one of the largest strike-slip earthquakes ever recorded, and it proved that the Atlantic is fully capable of producing world-class 8.0 plus magnitude quakes. The new study indicates that the locked segment on the Charlie Gibbs Fault has now accumulated stress far exceeding what was released in the 1941 event. It is, in effect, a time bomb. But what truly makes this a catastrophic threat is not the shaking alone. The greatest danger is the secondary effect. A common misconception is that strike-slip faults, which move horizontally, cannot generate large tsunamis. This is technically true. They are inefficient at vertically displacing the seafloor. But the Mid-Atlantic Ridge is not flat. It is a steep, jagged, and highly unstable mountain range. The violent horizontal shaking from a magnitude 8.0 quake in this region is the perfect trigger for a completely different kind of disaster, a catastrophe submarine landslide. A multi-minute rupture on the Gibbs fault would shake these unstable volcanic mountains, dislodging billions of tons of rock and sediment from their steep underwater flanks. This would trigger a massive flank collapse. This displacement of water would generate a massive flank source tsunami. Because this event happens in the middle of the Atlantic, it creates a unique and terrifying hazard, a transoceanic tsunami aimed at 4 continents simultaneously. Sophisticated models show the wave radiating outward from the North Atlantic. To the east, it would devastate the coasts of Ireland, the United Kingdom, France, Spain, and Portugal. To the south, it would threaten the Azores. But the most significant threat would be to the west. Traveling at the speed of a jetliner, the waves would cross the Atlantic in approximately 6 to 8 hours. By the time they reached the North American continental shelf, the waves would still be a catastrophic wall of water, potentially 10 to 20 meters high. This would overwhelm the coastlines of Newfoundland, Nova Scotia, and the entire U.S. East Coast, threatening major population centers from Boston and New York City down to Miami. This new scientific study transforms our understanding of the Atlantic. The Atlantic crack is not a quiet, gentle divide. It is a violent, complex boundary, webbed with hidden San Andreas-style faults that are locked, loaded, and capable of triggering a disaster that would span the entire ocean basin. We often look to the Pacific Ring of Fire for the planet's greatest geological threats. This new data is a chilling reminder that the Atlantic holds its own dangers, hidden deep beneath the waves, waiting for a single rupture to unleash its stored energy. If this analysis gave you a new perspective on our planet's hidden forces, please like this video and subscribe to Geology Watch. Join us as we continue to explore the incredible forces shaping the only world we call home.